If you're doing any kind of modern infrastructure assessment, you're probably going to encounter containers, and you'll probably land shells within those containers. If you don't understand what a container actually is, then you're going to miss half the attack surface. Most people know the security plus answer, that the host and the container share the same kernel, but that doesn't really give you a good mental map of how you can think about escaping the context of the container to exploit the host. So that's what this video is about. We're going to go deep on what a container actually is from the perspective of the kernel and how you can go about assessing containers and breaking them. Let's start by looking at a process. So most of us are probably already familiar with what a representation of a process memory map looks like in Linux, with the stack, the heap, and these other memory regions. And one of these sections of process memory is only accessible to the kernel, or ring 0 execute. Within this memory reserved for the kernel, there's a data structure called the task struct. This is the kernel's representation of the running process. So everything the kernel needs to know about a process lives here and is reachable from here. Its state, its scheduling information, file descriptors, credentials, and so on. When people say containers share the same host kernel, the difference between a containerized process and a regular process isn't what kind of process it is, it's the values of the few specific fields within this task struct. There are two areas of this task struct that matter for container security. The first is the nsproxy pointer, and this controls what the process can see. And the second is the credentials and capability sets, and this controls what the process can do. So let's start with namespaces. The nsproxy struct here holds pointers to 7 different namespace objects. So every process on the host that isn't containerized shares the same namespace objects, the initial namespaces that were created when the kernel first booted. But when Docker starts a container, it creates new namespace objects and points the container's process's nsproxy at them. Everything else about the process runs and behaves the exact same way. It just holds different pointers to different namespaces. So let's go through these 7 different namespaces. The PID namespace controls what other processes a process can see and signal to. And when Docker creates a container, it creates a new PID namespace. The first process in that namespace, or your container's entry point, becomes PID 1 in its own process tree. And this is a pretty critical point to understand because on the host, the same exact process has a completely different PID. So depending on which PID namespace you're looking from, they'll be referred to with different IDs. The mount namespace controls what file system a process sees. So each mount namespace has its own set of mount points. When you're in a container and you try to list out the root directory, you see the container's root file system. The host real file system is hidden from you. So the mount namespace struct holds a list of mount structures describing every file system mounted in that namespace. The container gets its own list starting with the container image's root file system. The network namespace isolates network interfaces, routing tables, firewall rules, sockets, and every container gets its own loopback interface and nothing else by default. When Docker creates containers, it does a few extra steps by adding a virtual interface that can network containers together. But in principle, when you create a new network namespace, nothing else is really in it. The UTS namespace is pretty simple. It's just about isolating the host name and the domain name tied to the system, so you can change the host name within the container. And the IPC namespace for inter-process communication, it affects what memory segments, semaphores, and other data structures the process can read from and write to. The user namespace is pretty interesting from a security perspective because it's a map of what users within the containers map to what users on the host. So this is why rootless Docker containers exist, and a root within a container can map to a specific unprivileged user within the host. It's important to note that this behavior isn't default when you create a Docker container, and the root user in the container is actually the same root user on your host. And it relies on other mechanisms that we're going to get into to actually create some sort of a security boundary between the two. And finally, the cgroup namespace. This will change the view from the container's perspective of what resources are available to it. So this is how you would tell a container that they only have, for example, 2 gigabytes of RAM to use, rather than the 16 gigabytes that your host actually has access to. So I'm going to stop talking and let's create a sort of manual container using the unshare utility, which just calls the unshare syscall. So on our host here, I'll just gain some context and we'll see some processes, see the host name, and our network interfaces. So like I mentioned, we're going to use the unshare utility, so we can learn a bit more about this with its man page. And a lot of this will show exactly what I was talking about earlier, the difference between all the namespaces. And these options down here are what we're really going to be focused on when we're creating our own container. So first I'm going to create a manual container with just a new PID namespace so we can see what that looks like. But first I'll give some context as to what our current process tree looks like on our host. And then I'm going to go into a new terminal here and use the unshare utility. And we're going to want a new PID namespace. And as you may have seen earlier, only the new PID namespace will be used by children of this initial process. So we need to use the fork flag along with that. And then we're also going to create a new virtual file system at /proc, as that will let tools like PS actually view our new process tree. And we're going to set our entry point as a bash shell. So when we hit enter, it looks as though nothing happened, but actually we now have this new PID namespace. So when I look at all the processes that are running, we're only able to see bash, our entry point with PID1, and the PS utility I just ran. So let's take it a step further and exit this manual container. And this time we're going to run the same unshare command with a new UTS namespace and a new network namespace. Again, it looks like nothing happened. I'll show our new process tree. And we can also set a new host name. And when we get our host name, we can see that it shows anything, but it doesn't affect our host system. We can also see the IPA that only the loopback interface is available when our host system has a lot more. So this is cool and everything, but it doesn't really feel like a real container since we're still able to access the whole host file system. So let's unpack a file system from the Alpine container, for example, and then set that as our mount point when entering the container. This is a lot of the things that Docker will do automatically for us once they've created the new namespaces. Let's go here. Let's make a directory for our container. And we're going to run this command, which will just create a new Alpine container and save the file system for us. Okay, so now if we look at emp container, we see that this is a valid root file system. We're going to run unshare again, creating a new PID namespace, same as before. Also net, C, UTS, and mount. And as soon as we enter this context, we're going to run a few extra commands. And this is what Docker would be doing on your behalf when you start a container, which just allows us to enter that new file system and isolate the file system from the host. So now we can list out directory here, and just to prove that we're in a different root file system, we can list out home and see that there's no home directories for our users here. And let's see the host name, anything, and network interface, and process tree. Now let's look at the second area of this task struct that matters. So the difference between our unshare container that we made and what Docker actually runs mostly comes down to these three things: capabilities, seccomp, and AppArmor. These are the actual security controls. So namespaces control what you can see, but these control what you can do. Linux has about 40 capabilities that break root's privilege into discrete units. So process doesn't need to be fully root, it can just have the capabilities that it needs to perform its function. For example, app-net bind service to bind to port 80 without needing full root privilege. Docker's default capability set drops many of these capabilities from what a full root user would be able to do. So things like capsys module for loading kernel modules, capsys ptrace, capsys raw IO. They're not needed by most application containers, and each one is giving us a potential escape vector to then access the host from within the container. Let's see what this looks like when we run a Docker container. So we're going to run an Alpine container. And when we're in the container, we can look at the capabilities granted to the process, for example, the shell. versus what we're able to do as root on the host system, you can see that all of the bits in this capability bitmap are set to 1 in our host file system root, and in the container root we have a lot less capabilities, or a lot less switches turned on for our capability bitmap. You can also see that our host system has a 0 for seccomp, meaning that there's no seccomp profile loaded. And in our container, you see that it is marked as a 2, which means there's a profile active. And let's do the same thing for app armor. So it's unconfined on this system and has the Docker default profile within the Alpine container. So how do all of these different mechanisms fit together to create a security boundary? So you can think of it as namespaces control visibility, or what you can see. Capabilities control privilege, or what root level operations you can perform. Seccomp controls syscalls and which ones are available to you or blocked. And app armor controls access, so what specific resources based on file path you're able to alter. That's all I have for how containers work and the security mechanisms in place for them. And to practice some techniques of breaking out of them, I created what I called Escape Pod, or a 5-level bandit-style wargame challenge. And I'm going to walk through just one of the levels, as it's probably the most important escape technique that you'll run into in the real world. And I'll show you how to set up Escape Pod and try it out yourself. So you can go under the Releases tab on GitHub and download this qcow2 file, which will be a VM image that you're able to run with qemu. Once that's downloaded, you can come back here and run this command once you have qemu on your system, and run it, changing the drive file to the file location you downloaded the qcow2 file. Now it's booting. You can go to a new terminal and SSH into level 1. Password for level 1 is escape pod. Now we're in. And I'm just going to skip level 1 and go straight into level 2. So pretending we just solved level 1, we have the next password into level 2. And it says this container runs the infrastructure backup agent and monitors running containers and ships snapshots to S3. It gives us a config file, a log file to look at, hint file for guidance, and solution for the answer. So regardless of the scenario here, one of the tools that you'll definitely want to add to your tool belt for assessing containers is this deepc script, which you can think of as like the WinPs or LinPs of containers. I'm going to grab that and get it saved in the container and run it here. So it ran. I'm just going to scroll up, and it says that if something is exploitable and very important, it's highlighted in red. So some of these are important, and this is what we want to pay attention to here. Docker sock mounted, as this is probably the most common misconfiguration you'll see. It mentioned that this container was responsible for monitoring other containers. So what it does is it mounts the Docker socket into the container itself, allowing you to run Docker commands from within the container. So a lot of people don't realize that when you run Docker commands and you're talking to the Docker socket, that process running the socket has a much higher privilege level than the process that's running within your container. So for example, when we run a new container of Alpine, and we can mount the root file system to /host within the container, and then our entry point will be changing our root file system to this /host and setting bash as our entry point. So now we're within the new container, and when I list out the contents of the home directories, see that there's 5 levels. This is the VM file system that's running these different containers representing our levels. And we can go to /flags and get the password to level 2, which we can use to log in to level 3. So that's all. Hopefully you go and try Escape Pod and let me know what you think. And if you do so, then maybe I'll add a few more levels to cover some more general container escapes. And I'll see you next time.